Good morning, everyone. Welcome to this part of the webinar. This is going to deal with the electrical hazard known as arc flash. My name is Jeremy Gadd. I'm the Managing Director of Covol Engineering. We provide electrical engineering services to industry, work with a number of large and small companies in the UK and further afield. We provide electrical engineering services such as network analysis of electrical distribution systems, including power and load flow studies, earthing, protection coordination, switchgear risk assessment, and of course arc flash. Now in our fifth year of operating, we've conducted up to probably now on 1,000 studies of various sizes across many different types of industry. We're proud of our heritage and skill set and the experience that we have in our electrical engineering team. Today I'm going to take you through a number of different topics, all relating, coming back down to arc flash. These are going to provide you with a background and understanding of the phenomenon known as arc flash, starting with the well-known hazards of electricity and then ending on the risk assessment process, where there's a lot of information on a slide because some of them are quite busy. I'll leave a little bit of time for people to read. Anyway, so moving on. The hazards of electricity. So in terms of electricity at work regulations, HSI 25 is the guidance document issued by the HSE covering electricity at work regulations 1999. And these regulations cover all of UK industry, and really every electrical engineer should have or be aware of this guide as it sets out the requirements and expectations in managing electrical distribution. And you can see on there's a number of examples that define the term injury, which will be discussed in the next few slides. For the purposes of this session, it's electrical arcing is what I'll be focusing on the most. Just in terms of electric shock and burn, the text here is taken from the HSE's website, and the details describe the effects of electrocution of the human body and injuries such as burning and muscle spasms as the result of being in contact with live conductors at low voltages, whereas at higher voltages, the consequences will be far more severe and likely to be fatal. We mentioned in the previous slide about electrical fires. So this information has been taken from the UK government statistics and insurance data sources. And although domestic fires are in decline, 35,000 in the last recorded year, 2019, 2020, and is the lowest number on record. The highest number of electrical fires was some 20 years ago now, but the prime cause of electrical fires still remain the same. Electrical appliances, and more significantly, electrical distribution being jointly the second highest cause of domestic fires. When it comes to electrical arcing, flashover, arc flash, which we'll discuss later and more in depth later, this is a catastrophic event that at best will leave you with irreparably damaged equipment, at worst, significant and possibly fatal injuries. Our experience has been that we tend to find significantly damaged equipment. Unfortunately, people are far enough away or completely out of the area when these things happen. But you can see that the damage in the few slides, and I'll show you in a little bit more detail the effects of electrical arc incidents. And finally, with electricity, I think everybody remembers the Buncefield explosion 20 years ago now. The explosions caused by electrical ignition completes this list of hazards. The DESIR regulations cover the requirements for the management of flammable explosive products used in industry, the means to assess, manage, and mitigate risk. So there are the 5 main hazards of electricity with respect to people and industry. So now with a little bit more detail on where this webinar is focused on, which is about arc flash and electric arc, it's been depicted on that image there. And we start with the 2 central bars, which are the conductors, and we end up with, in the event of an arc flash, This simple depiction shows a number of events that happen very quickly during an arc flash. You have electrically charged gas, which is the plasma, and that's emitted and further supports the production and duration of an arc. Ultraviolet light and infrared radiation are emitted from the arc center, and the resultant explosion and the production of heat results in the vaporization of copper, plus bars or other molten metal and shrapnel being emitted, along with pressure, which is a blast wave, and sound waves being emitted. That is very, very destructive. Some of you might be wondering if there is any difference between a short circuit fault, as in a bolted short circuit fault, and an arc flash, and the answer is yes, there is. With a bolted short circuit, there's zero impedance and the full short circuit current flows with no energy being liberated at the fault. In an arc flash, the arc has impedance and around 50% of the short circuit current will flow through the fault, delivering an enormous amount of energy as depicted in the previous image. There are numerous causes that can lead to an arc flash event, and I've listed some of these on screen now. Staff competency and low or no awareness of the hazards, poor maintenance and improper conditions all contribute to the cause. So generally, I wouldn't necessarily say it's ignorance, but it is around poor knowledge, poor maintenance, and just a general lack of information relating to arc flash hazards. So when we look at the consequences of arc flash, there are a number of videos that show arc flash events, none of which, by the way, I've used in this presentation. And those of you who want to see the effects on people, if you just type in the arc flash injuries and select the images, you can see examples of the types of burns that can be inflicted on people. And note that these images that you'll see aren't for the squeamish. As for equipment damage, you can see there are two cubicles there that show the after effects of an arc blast or an arc flash incident. They are, extremely catastrophic. I'm now going to move on to how we start to address the issues of arc flash and some of the main principles in managing electrical distribution systems. I've divided these into three areas. We've got safe systems of work, competence, and electrical equipment itself. So with safe systems of work, it's a fundamental requirement in any work activity. And when working on electrical systems, these are just a few of the topics that should be in place in order to work safely and minimize hazards resulting from electricity. Hopefully, you'll recognize a number of those topics on there and have them in place. In terms of competence, and specifically Regulation 16 of the Electricity at Work regulations, the competency of staff who work with electrical systems of paramount importance, has been said in previous slides, a point which I'm sure you're all aware of, and I can't stress enough the importance of having suitably qualified and experienced personnel working on electrical systems. As mentioned, this is a requirement under Regulation 16, Electricity at Work regulations. And there is also a need there for an annual review to ensure that competency is being maintained, whether that's through on-job audits or whether it's through some other similar experience-based recording system. When we look at electrical equipment, it's maintaining and keeping electrical equipment safe and in proper order starts when the equipment is first installed, and this life cycle is an important part of ensuring that equipment remains in optimum condition throughout its installed life, so that it operates and behaves in a manner that reduces the risk of incidents. We can easily divide electrical equipment into two basic categories, and those categories are normal operation and legacy operations. So when we come to equipment that we define as normal, it's the type that's looked after, cared for, managed to a standard that's defined by the manufacturers, and the potential for a hazard is generally lower than that of legacy-based equipment. Legacy equipment will need far more care, attention, and respect. This is due to its older age and potentially lower reliability. As with all equipment that is perhaps past its end of life, people do become complacent when they start to address any issues with it, because it's always been there and this is what we do and this is how we do it. And it also can be a factor when dealing with this legacy equipment. It's one of those things that you need to be aware of to make sure your staff, engineers, electricians, and so on don't fall into that trap where this is what we've always done. So in summary, these three factors should be included in any electrical safety management system and will all make a positive contribution to ensuring that risks are reduced when dealing with electrical equipment. So now we're going to move on to the topic of risk assessments, of which I'm sure everyone has heard of and conducted their own. The Management of Health and Safety at Work regulations makes a clear statement on assessing the risks to employees and anyone not employed that may be in or working or near work being carried out. As we all know, risk is a result of likelihood versus severity. So when we look at take an example of a typical cycle here, showing the process of risk assessment, when applied to electrical safety, more specifically in arc flash, there are a number of factors that influence the likelihood of harm, plus a similar number of factors that influence the severity, shown on the right-hand side. We've previously discussed the factors influencing likelihood, such as their systems of work, competency, and the equipment itself. And we'll now look at those that contribute to the severity. Incident energy is defined as the amount of thermal energy impressed on a surface at any given distance during an arc. The distance, here defined as the working distance, is that between a person's face and chest area and the source of the arc. Both of these terms are defined in the standard NFPA 70E. The units of incident energy are generally expressed as calories per square centimetre. So what affects incident energy? Well, incident energy is a combination of the amount of current and its duration. The diagram shows a very simple distribution system from the transformer to the sub-distribution boards. Protective devices which limit the amount of current resulting from a fault play a significant part when determining incident energy and understandably affect fault levels at sub-distribution levels. When assessing distribution systems for arc flash, incident energy values can be determined at any point in that electrical distribution system. Look at the severity. So this chart shows the relationship between incident energy and fault current. And this is using 600 volts empirical data. As you can see, the relationship is approximate to a linear one. And the IEEE 1584 standard, which we'll come on to later, uses this relationship in arc flash calculations. But note that this relationship, this calculation is only used up to 15 kV. Anything after that is used the Lee's method. Ralph Lee produced a set of empirical data, and over 15 kV, 15,000 volts, that's the point where you start to use this Lee data. In terms of boundaries, once the incident energy levels have been determined, arc flash boundary can then be determined itself. The boundary is a distance where incident energy levels are equal or less than 1.2 calories per centimetre squared. The basis for this energy level is from experimental results obtained by Stoll and used to determine the rate of tissue damage. You can see there that the lighter with a naked flame, you put your hand over a naked flame and you're going to start to sort of burn flesh, and that's basically what that piece of work determined by Stoll. So now if we return back to the calculations, and typically the IEEE 1584 standard, which was mentioned earlier, the calculations used in determining the hazards resulting from an arc flash incident are detailed within this document. There are a number of websites that can calculate these figures too. But I'll conclude this slide by saying that there's an old proverb that goes along the lines of a little knowledge is a dangerous thing. I can go and probably watch a number of videos on YouTube on going how to build houses and how to build roofs, but that doesn't necessarily make me a roofer or a house builder. So it's one of those use at your own risk. So a typical arc flash study consists of a number of different sections. And each one, plays a separate part in compiling the end result. Everything from data gathering through to conducting the fault study, determining what boundary calculations are, doing the risk assessment, and then looking at what risk control measures can be put in place, whether or not protection study is needed, and then if necessary, training and implementation. The output of the exercise is a report detailing the worst case findings. Because obviously with this, it's always about the worst case. This is, it's the if question all the time with arc flash. If it does happen, this is what is likely to happen. It is a risk assessment. So we end up with the labelling, which determines what the results of that arc flash study have determined. And this denotes incident energy levels and arc flash boundaries. Once incident energy levels are known, then appropriate PPE can be specified. And there's note there that they use cotton underwear and FR shirts and pants. Well, that FR is now known as AR. FR was fire rated. That text now has been changed to AR, which is now classed as denotes arc rated. But these are typically the labels that you would see on switchgear following an arc flash hazard assessment. And this gives the guidance that's required along with the typical PPE requirements, distances, and the incident energy levels. So when we look at mitigating risk, the use of that well-known hierarchy of controls is one of the most accepted methods in use. Supported and championed by the HSE, it uses a number of steps, with each one slightly less effective than its predecessor. Apologies for these next few slides, as there tends to be a lot of information on, but I will try and cover it all. So, elimination. The first approach is to consider is to take away the hazard completely. Not always practical, because the requirements in electricity work regulations, those legal requirements with respect to working dead, and consider remote switching. And although this minimises the risk to personnel, it doesn't alleviate the risk of damage to switchgear. So in other words, you can take the person away, but if the arc flash event still occurs, you are likely to see fundamentally damaged switchgear. And also note the two publications, HSG 85, which is Safe Working Practices, and Electrical Safety First, Best Practice Guide number 2, which is Management of Electrical Safety and Safe Isolation Procedures. Two very good sources of information. And I didn't know Martin was the previous speaker. There are other publications available just to avoid any conflict of interest there. The next one is substitution. If you recall from a few slides back, reducing the time or the current will reduce the incident energy levels, and adjustment of protection settings will go some way in achieving this. Next up is engineering controls. And this may prove difficult to achieve given that equipment is already installed and in use, although there are some points on here that may prove beneficial to some. With awareness, competency will always be a mainstay of electrical safety, and the use of labelling and pre-job briefings, but be aware of any sort of complacency being set in, can go a long way in reducing the likelihood of an arc incident, and more importantly, the consequences of arc flash incidents. So whether this is specific arc flash training, whether this is on the job training, job briefings, labelling, warning notices, it all helps for that awareness. I mentioned safe systems of work in earlier slides, and it's here where they sit in terms of the hierarchy of controls. The use of generic permits to work is frowned upon, as the electrical hazard definition tends to be very vague and often results in the use of the phrase own isolations mitigation step. Be sure to use separate systems for electrical work so that hazards are defined and more appropriate for the type of work being carried out. The publication shown is HSG 230, Keeping Electrical Switchgear Safe, and it's another very useful and informative read. Again, it's another one of those HSE documents that electrical engineers, electrical people should be aware of. So finally, we end on PPE, also known as the last line of defence. PPE doesn't do anything other than do its best at protecting against injury and harm. With arc flash, there are categories of PPE based on the calculated incident energy levels. And here at Covol, we always recommend Category 2 workwear for staff involved in daily electrical tasks. Arc flash PPE categories range from Cat 1, which sort of doesn't exist by virtue of the fact that there isn't the need for Cat 1, through to Cat 4. And there are several reputable suppliers who can supply and provide guidance on their upkeep. And just as another note, there is PPE available above Cat 4, the incident energy levels that Cat 4 requires. But we wouldn't recommend use of this due to the blast pressure waves and the sound waves that happen as a result of an arc flash event. So Cat 4 PPE is the sort of moon man suit, you know. I'm sure some of you may have seen the film called Hurt Locker, where the diffusing bombs. And if you imagine that suit that the guy has to go and wear, it's not too dissimilar from that. Finally, the standard that sort of overreaches arc flash, which is where it's probably the most recognised standard that's used, and that's NFPA 70E. It's the guidance that's predominantly used in carrying out arc flash assessments. It's updated on a regular basis, and it provides valuable insight into arc flash hazards and includes a number of the definitions that are being used in this talk, including risk assessments, the hierarchy of controls, and how electrical equipment is defined when carrying out assessments. So I've made reference to a number of different documents and standards and publications that are available. Those are the ones there, and as you would imagine, a lot of them are HSE driven. Believe an arc flash incident would be RIDDOR reportable because it's an electrical fault, potential electrical fire. And as is the HSE's case, they will always expect you to have applied best practices that relate either to British standards or the likes of health and safety guides or other documentation and standards that is around and available. So in summary, there's a few main points I'd like to make. Arc flash hazards do occur. They aren't all that frequent, but when they do, the consequences are generally catastrophic. The lost production is something that most businesses can possibly get over, but the loss of staff or visitors, the loss of reputation, or even hefty fines can signify the closure of a business. Managing the risk by having arc flash assessments carried out is always going to be a good start. If, in the event that arc flash assessments dictate that the hazards and the risks from them are still too high, there are some other alternative measures that can be taken, and these are typically around switchgear risk assessments, where we look at what risk is as a result of arc flash, and there are sometimes ways and means where we can actually make remedial actions and reduce potential hazards. So, we're Covol Engineering, and thank you very much for your time. And if there's any chats or any questions, I'd be more than happy to answer them.
Perfect. Thank you, Jeremy. We currently don't have any questions from the audience. I will be honest, I'm not an expert when it comes to arc flash. I write about the industry, I don't work in the industry, so it's just a very hard subject to grasp.
It is, John, you're right. It is one of those subjects. it was relatively niche. I think more and more people are becoming aware of the issues that arises. As I mentioned, the accidents themselves or the incidents themselves are quite rare, fortunately. However, it's one of those things that in any sort of corporate environment, you need to consider the risk of those happening, and it's entirely down to the business as to whether they see it as an issue. It may be that electrical engineers have a good understanding or a good handle on how they think, or whether they think that the risk is present or not. But I think everybody should at least consider the need for arc flash assessment. It is a significant hazard when it does happen.
Yeah.
And there are a number of different providers of arc flash around the UK. America is dominated by arc flash. That's where the NFPA standard comes from. And so they're a lot further ahead than what we are. Whether that makes them any more safe is a matter for discussion, a matter for debate. I think with the UK, though, there's never been any specific guidance or any specific regulations. However, if you do read the electricity work regulations, it does make reference to electrical arcs, and that, the electricity work regulations has been out for a number of years. So in the UK, the HSE recognise it. I think it just wants popularising a little bit more.
So what more do you think the government needs to do in order to?
Well, I think it's not necessarily government.
Okay.
I think this is all around awareness, because the hazard is out there, the regulations are out there.
It's just people aren't necessarily aware of them.
Correct. Yes. Yeah. Correct. Yeah.
Perfect. Is there anything else you would like to add?
No. Thank you for listening. It's been very enjoyable. Thank you for your time, Jordan, and thanks for having me on here.
Thank you for joining us. We really appreciate it.